Yeah, okay, it looks like you're recording. Okay,
Yeah.
so today what we're going to do is start off by taking a look at the end of the theory of chapter 7. So we've gotten, if you'd have your lecture notes at hand, we'd reached the theorem on inversion of functions. So we now know that when we have a bijection, we can invert that function, and that a certain number of properties then translate onto the inverse function, and we can even compute the derivative. Okay, that was the object of theorem 742 that we've used quite a bit. So we've studied the inverse of tangent, sine, I think, and probably hyperbolic sine, and we'll study the inverse of many more functions in the next few days. So we studied arctangent, and we've got a little bit of the chapter 7 remaining, with some theorems related.
Wait, are you speaking at the moment?
We can't hear you. There must be a problem because I don't think anybody can hear you.
I think I've got internet issues as well. I might need to. Where is it, Tristan? Okay, looks like you're recording. Okay, let's try again. So I was here. Okay, can you see the screen okay this time? I'm hoping you can.
Yes.
Okay, so I'm on basically page 100. No, actually I'm not, because I've got a different numbering system now. Wait a minute. I'm on page 117 basically of the notes, and continuing on things related to differentiability. So what we've seen so far related to differentiability, if we take a look at the lecture notes, is how to inverse a function. We know that under certain assumptions on a function that's monotonous, you can define the inverse of a function, and a lot of properties of your original function, if you can inverse it, sort of translate to the inverse function, and it's allowed us to define things like arctangent, inverses of some polynomials, probably arcsine and argsh, I think, and we're going to see some others, but that was one sort of key part of the notions related to differentiability. And what we're going to see today is the end of the theory, I guess, related to chapter 7, and we're going to go further with things related to differentiability. So what I was writing was, first of all, some things related to minimums and maximums of functions. So what we're going to do is find some properties that link differentiable functions with minimums and maximums of functions. And so what I was talking about when I was writing all of this was the idea of a local maximum or a local minimum for a function. So generally so far, if you've ever talked about minimums or maximums for a function, so for example, you could talk about the minimum of x squared behaving roughly like this. You'd probably say that 0 is a minimum for x squared, and what it is actually, it's a global minimum. If you take the function x squared on the whole of R, it's always above 0, basically. So that's something called a global minimum, but we can define something that's quite similar called a local maximum or a local minimum. Now on this sort of squiggle type function that I've just drawn, you can see that the function goes up and down, up and down, up and down. And at various points, I've indicated that we may have a local minimum, and at other points, you've got a local maximum. For example, if we take a look at this point here, what happens with this point here is that if, for example, we take the interval on R that's roughly around here on the x-axis, this point is greater than the images of all of the these points, which are roughly this part of the curve. So this is a local maximum for the function. It's not a global maximum. For example, this point here is much higher than this point, but we can find an interval for which this point is a maximum. And similarly, we can find local minimums, so this one, and this one. So a local maximum or a local minimum equally is a point of your x-axis for which around that point, so on the neighborhood of that point, all of the sort of values for the function are either smaller or bigger than that point, depending on whether you're a maximum or a minimum. And you'll be strict if you have a strict inequality here. And so this contrasts with the global maximum or global minimum definition. Here we only need this f of x smaller than f of a to hold on a neighborhood of your point A. Global maximum is when it holds basically on the whole of the interval that you're considering. So here, local, it's x in I, but we restrict to any x on the neighborhood of A. And global maximum, you have x in I, and for all of those x's in I, you have f of x smaller than f of a. So we can generalize the notion of an extremum to a local sort of setting. And one thing that we're going to look at is one way of characterizing maximums and minimums. So if you look at this curve, can you tell me what happens to the slope of the function at each of these points?
It becomes 0.
Yeah, absolutely. So a really important thing, if you look at a function that's maps from R to R, for example, whenever you have a minimum or a maximum, if the function is differentiable, of course, the slope, so f prime of the function at that point, becomes equal to 0. Now, do you think that the other way round helps? So so it seems that at an extremum, and this is whether you're local or global, the slope of the function is equal to 0 if the function is differentiable, of course. Now, what do you think about the statement slope equal to 0 implies that you're an extremum, so either a minimum or a maximum?
It doesn't hold for the functions of the type x is equal to something or y is equal to something. Yes, it has to change of sign for it to hold.
That's a very that's a very good point. It doesn't. You're absolutely right in that this sort of rough statement that we'll define in a minute mathematically, the converse of it does not hold. So the converse does not hold. One important thing that was just mentioned that was, I think, hidden behind when you said that the function's got to change sign. Yeah, the slope of the function it's got to not only be equal to 0, but change sign. Your function here is decreasing and then increasing, so the derivative is sign is negative and then positive. And similar here, the sign will be positive then negative. And one way that you can see that it does not hold, it's an example that's in your notes. If we take x cubed at 0, if we take the derivative of x cubed, you get 3x squared. The derivative of this at 0 is equal to 0. So the slope is equal to 0, but 0 is absolutely not a minimum or a maximum for the function, because the sign of the derivative does not change on either side of that point. So one important link between a differentiable function and its extremum is sort of quantified in the following. It's just rewriting what was said previously a little more precisely. So if you take an open interval of R, you take a point in that interval, you need a differentiable function because we're going to consider the derivative. You have the following implication. If you're a local extremum at A, then f prime of A is equal to 0. And the converse is not true. X cubed is an example of that, but it's not the only example. Okay, so that's a first thing that we can do with derivatives of functions. And we're going to, what we can take away from this is if you're ever looking for a minimum or a maximum, you're going to look for them at points where the derivative cancels out. So it's something called a necessary optimality condition, which you'll see probably later on at INSA. If you ever look for the sort of maximum and minimum of your function, it will either be at the limits of your bounds or amongst points where f prime cancels out. But you need to check some extra things to then check whether you're a minimum or a maximum. But it helps a little. So we can see that finding points where the derivative of a function cancels out, can be quite an important thing to be able to do. And there's a theorem in maths that gives some conditions under which such a point will exist. And that's those conditions are called Rolle's theorem, which is another one of the key sort of analytical theorems of this chapter. So we can take a look at what Rolle's theorem tells us. What we're going to consider are A and B two real numbers. And we're going to take a function that maps from the closed interval AB to R. And so we're going to suppose that f is continuous on the closed interval, differentiable on the open one, and f of A is equal to f of B. Then in that case, you can find C in between the 2 points such that f prime of C is equal to 0. We can illustrate that as follows. So one example of a curve that satisfies this. If you have something like this, suppose that that curve is the curve of a differentiable function. If we put A here, B here, then here, for example, we have C. This would be f of C, and we'd have f prime of C here equal to 0. Okay, if you have a continuous function that goes through basically these 2 points and everything's differentiable, there's always going to be, to join these points in a sort of smooth way, so sort of continuous and smooth, you've got to at some point, if you go down, you've got to come back up. If you go up, you've got to come back down. And if you don't go up or down, you've got to be constant. And if you're constant, then the derivative will be equal to 0. So it's quite an intuitive theorem, I think. The proof is quite nice to look at. So we can look at the proof, which is in your notes, and I can comment on it a bit. So let's have a look at how it's proven. So the first thing, it says the result's trivial if the function f is constant. What is how is it trivial? Do you know, how could you, what would you write to prove the result if the function is constant?
Maybe that for every x in the domain, f of x, for every x and y in the domain,
Yeah.
f of x equals y of x, which implies f of x is is less or equal than f of y.
Yeah.
And so that
You're almost, yeah.
and then that the derivative is equal to 0.
Yeah, absolutely.
I think that's it.
Yeah, that's exactly what you want to prove. So if you have a constant function on your interval, then if you take any 2 points in the interval, the values are equal. So here, here we have, in particular, if you take f of a and f of b, they'll satisfy this property. And also, as your function is constant, you also have f prime of x and f prime of y equal to 0. So it writes really quite simply from the fact that your function is constant and continuous and differentiable. So that is just from the definition of the constant function. So with that in mind, we can suppose that the function is not constant, okay? And we'll use the fact that it's not constant to do the proof. So the first thing is that we've supposed that the function is continuous on its interval. And as it's continuous, using some theorems that we saw either earlier this week or I think maybe even last week, we can say that the image of AB by the function f is equal to a certain interval, M capital M, where the smallest value M here is basically the minimum of the function. That's attained because the function is continuous on a closed interval. And the maximum, the biggest value here is the maximum of the function, which also is attained because the function is continuous on the global interval, on the closed interval, sorry. So as it's continuous on a closed interval, we've got the following sort of image set for our function. And what we've supposed is that f is non-constant. Yeah. Was somebody about to say something? Okay. So f is non-constant. As it's non-constant, then we've got two possibilities. Basically, there's no straight line linking f of a and f of b. The function has to vary somewhat. So you've got either f of a is not equal to small m, or f of a is not equal to big M. Okay, can you still hear me?
Yes.
Okay, no, it's just a bit okay, a bit worried that it wasn't the case. Okay, so we've got either of these two possibilities, and so we can suppose that one of these two holds. So we're going to suppose if we're at the left-hand side of the interval, so f of a, for example, here, f of a is not equal to the maximum of the function on that interval. And what can we say from this? We can say, using one of the continuity theorems again, that as m is not equal to f of a, you can find some point c in the interval such that f of c is equal to m. Okay, so the function at some point on the interval between a and b is going to reach the maximum m, and what we can then compute is at c we can compute the slope or the difference quotient of the function. So the function is differentiable at c, so f prime of c exists, and as it exists, and as we're at a point that's in the middle of the interval, we can write the left-hand and right-hand limit of the difference quotient. And what we want to prove is that this thing here is equal to 0. So we're going to be able to prove that, we need to use the fact that f of c is equal to m is equal to the max for x on AB of f of x. So what can we say about the sign of f of c plus h minus f of c. As f of c here is equal to m, and m is the maximum of the function.
It goes to 0.
It does go to 0, yeah, but we can say something about the sign of this.
It's
The sign of-
positive.
I think it's negative in this case.
Oh,
But
and the
I think
other one
you had exactly the right idea. What we have is for any x on AB, f of x is smaller than f of c. So f of c plus h minus f of c is negative. Okay, c plus h is not quite at c, it's some point around c, and in particular it's in AB. So f of c plus h minus f of c is negative. And so the limit when h goes to 0 plus of f of c plus h minus f of c divided by h. What's the sign of this limit?
negative.
Absolutely, yeah. So that's negative. And if you take the limit where you take h going to 0 minus, what do you get? So this is negative. And in this case, h is, I'm going to 0 minus, so going to 0 from the left-hand side, so in particular it's negative. So what's the sign of this limit?
Positive.
Yeah, absolutely. So if we take a look at what that means, if I just shift this, we've got two equalities. You know that f prime of c, as your differentiable at c, it's equal to the right-hand limit and it's equal to the left-hand limit. And we've got two different signs for f prime of c. So what can we deduce from that on basically f prime of c for it to satisfy these two inequalities?
That it is equal to 0.
Absolutely, yeah, perfect. The only way that both of those inequalities can be satisfied is if this holds. And so what we've proven here is that we can find some c such that f prime of c is equal to 0. And we've taken, I think, one of these two cases, and if you take the other case where m is smaller than, if not equal to f of a, small m, and you have the same reasoning with a minimum. But yeah, there we have the proof that you can always find a point where the slope's equal to 0, and you just need to have this type of drawing in mind. And one thing that we can note about it is that c is not necessarily unique. There we go. So in your notes, there's an example with applications to roots. In fact, we're going to, I think, apply this to roots of polynomials, and I think do one of these or both of these questions in tutorial exercises. So we won't apply that to roots just yet, but we'll do that, I think, next week in tutorial classes. So what's really important with this theorem is that you keep this type of drawing in mind, and you bear in mind that you don't generally have a unique point such that this thing holds. Maybe one side note that we can say here that I won't write. Imagine you've got a convex function, okay? You've got a function that goes from a to b, that's convex and differentiable, etc. Can you say anything about uniqueness if it's convex?
think that it is unique if it exists, because convex means that the second derivation sign
Yeah,
is always positive,
yeah,
and so the derivation sign, the derivation is always increasing, and if it's always increasing, it can only go once to 0, not multiple
Yeah.
times.
absolutely. Yeah, you're absolutely right. If you're it's something that I won't write here because it's not it's a little beyond, I guess, to prove it correctly, it's a little beyond what we do at the moment, but it's something that you can have intuition about quite nicely. So your reasoning with the second derivative is absolutely right. And another way of sort of just visualizing it is a function that's convex is a function that's always above its tangents. So you've got your sort of vague form of your function is going to be something like this, or like this, or like this. If you want to join A and B in such a way that f of A and f of B have the same value, and you can sort of visually see here with the functions that I've drawn that even, for example, no, that's not convex, but if I get it right, something like this, you've only ever got one minimum here, and equally if you're concave in these settings, you'll only ever have one maximum. So one way of ensuring uniqueness, but again, it's not something, I don't think it's written in the notes, is by adding some sort of concavity or convexity property. So yeah, you'll probably see that at some point. But that's something called Rolle's theorem, and it's a theorem that you need to know. You need to know that Rolle's theorem refers to that result, and keeping the sort of visual graph in mind is probably the best way to remember it, to be honest. With Rolle's theorem in mind, we can turn to another sort of, I think it's a last theorem related to differentiability. It's called the mean value theorem. So it's the last result, and it's another one that's quite visual. So if we first maybe do a graph, it's a graph that's in your notes, I think. But if we take some sort of function that maps between A and B, let me get this right. So we're going to take a function on an interval. We're going to take it continuous and differentiable. So it's got to be relatively smooth. And I'm going to draw it in such a way as to make my life easier. So something like this. Okay, so quite a function that doesn't do much between A and B. What we can do here is have a look at the slope of the line that goes from A to B. Okay, the line in blue just links f of A, which is here, to f of B. And what you can see is that if you sort of translate this curve this way a little, you can find a point for which a curve with exactly that slope is tangent to the curve of f. So what I've done is linked f of A and f of B. That gives us a line with a certain slope. And if you translate the curve a little, you can find a point which will be probably here, roughly. And at that point, this line here is tangent to the curve. And that's what the mean value theorem tells us. It's expressed as follows, and you've got the graph in your curve the other way round. It's expressed like this. So if you take A and B two real numbers, you're going to take a function that maps from AB to R. You're going to take it to be continuous, differentiable. And what you know is that f of B minus f of A here is equal to f prime of C times B minus A. And that's the mathematical way of writing the thing that we've just drawn here. So the mean value theorem is something that's quite useful in maths. One one of the uses for it is that if you're ever trying to express f of b minus f of a for some sort of, I guess, ugly function. Sometimes you can use this if your derivative is nicer than the function itself. You can use this to sort of simplify the expressions of f of b minus f of a. So that's one use for it. Another use for it is the mean value inequality, which you have in your notes that allows us to bound some objects. So it writes as follows. So the mean value inequality is sort of a direct consequence of the mean value theorem. So if you take a and b, two numbers, and we look at what happens under the same assumptions as the mean value theorem, so under this and this, and if we suppose that f prime is bounded on AB, then if you translate what it means to this inequality, basically this term here will be bounded, and so if you put the absolute values, you've basically got the absolute value of this term equal to the absolute value of this term. Then you can compute the product of f prime of c times b minus a with absolute values, and you get the product of the two absolute values, and then this absolute value will be bounded by this term here. So that's a nice inequality, and we can use it to prove some bounds. In fact, that's something that we're going to do quite a bit with the mean value inequality. So we can show that, we can use this to show that the following holds. So we're going to show that for any x that's positive, logarithm of 1 plus 1 over x is smaller than 1 over x. And we're going to use this inequality to do it. Okay. So one first thing that we can note is that we can rewrite this. If x is positive, can we say anything about the sign of this term?
It is also positive.
Yeah, absolutely. So this is strictly positive. So what we can do is say that logarithm of 1 plus 1 over x, as it's positive, that's equal to the logarithm of 1 plus 1 over x in absolute value. That, be careful, only holds if x is positive. If you're negative, then this term here becomes smaller than 1, and logarithm of something smaller than 1 is negative. And so we're going to want to exploit this, and we're going to want to use the mean value inequality to do so. So one thing that you can see here is that there are absolute values in the mean value inequality, and there are absolute values here. So we're sort of on the right track. But we're going to want to rewrite what's inside of the absolute value. So one first step is that we can rewrite 1 plus 1 over x as x plus 1 over x. Now, can I rewrite this further?
ln of x plus 1 minus ln of x.
Yeah, absolutely. So we get the absolute value of logarithm of x plus 1 minus logarithm of x. And can we now use this inequality on it?
Yes, with y equals y equals to x plus 1.
Yeah.
The opposite.
Yeah, no, yeah. It's just a bit annoying because I've got x and x plus 1 and y and x, but yeah, you're absolutely right. So what we have is for any x positive, logarithm is or rather I'll write things like this. ln of ln belongs to C0 on, so it's R plus star. Okay, so whenever you take any positive sort of points, you're continuous. And where is it differentiable? So if we want to apply the inequality above, we need the differentiability property too. So where's it differentiable?
Also an R star plus.
Yeah, absolutely. In fact, I probably could have written C infinite, but doesn't matter. So it's differentiable on R plus star. So in particular, it's, if we want to apply the theorem above, continuous on so we on x plus 1, if we take x strictly positive, and it's differentiable on x plus 1, x strictly positive, and for any x, or for any y rather maybe, or t belonging to x plus 1, ln prime of t is equal to 1 over t. And so now if we use through the mean value inequality, we've got this term here. If we use what's above, it'll be smaller than the supremum of the derivative between x and x plus 1. So smaller than the supremum of 1 over t for t belonging to x plus 1 times, where's the other term, times x plus 1 minus x. Okay, and what can we say about the two terms that are on the right hand side here?
It cancels to just be sub of 1 over t.
Yeah, you're absolutely right in that. It goes, this here is equal to 1, so it's smaller than supremum absolute value of 1 over t for t belonging to x plus 1. And what's this supremum equal to?
To 1 over t. Well, to the yeah, to 1 over x.
Yeah, absolutely. Yeah.
Because x is positive.
Yeah. That's absolutely right. So 1 over t, if you take it as a mapping from t to 1 over t, it's when you're on r plus, it's decreasing. So as t maps to 1 over t, decreasing on r plus star. So the supremum of this object here will be attained when t takes the smallest value, and so you'll take t equal to x. And so what we can say from this is that if we sort of look where we started with this term that we rewrote as this, and we've got an upper bound for this. So in fact, we've got an upper bound for that term here. So to conclude, logarithm of 1 over plus 1 over x smaller than 1 over x for x strictly positive. So that's an application of the mean value inequality, and we'll do a specific exercise on the mean value inequality a little bit later on, and we'll use it similarly to this again and show some other sort of nice bounds on different functions. But yeah, that's one example of how you can use it. And one other particular application of the mean value inequality.
Excuse me.
Yeah. Cool.
I just have a question.
Yeah. Yeah.
Why do we have an open interval for differentiability and then for the rest of the method?
Okay. Yeah. No, that's a good point. Let me just paste that before I don't. The reason why. Okay. The reason why is if you come back here, so the mean value inequality is a consequence of the mean value theorem. And so if you take a look at the mean value theorem, what happens with the mean value theorem is that the point basically at which this property holds, so the fact that f prime of c times b minus a is equal to f of b minus f of a, is not at one of the bounds of the intervals. Here, whenever you sort of link these two points, you have to shift the function a little bit in order to get this tangent here, this line here, sort of tangent to the function. So you're always sort of shifting this line to get a tangent, and so your point C, which satisfies this inequality, can always be found sort of strictly between these 2 points. And so the mean value inequality then, if you have a look at how it's proven, as a consequence of the mean value theorem, you get this here, and that's equal to this product. And that's always, this always holds with the C in between A and B, like this. So then when you turn to this theorem, if f prime of c is upper bounded on the open interval, which it is in many applications, then we get the mean value inequality. So the fact that you've got an open interval here is a consequence of the fact that the point here is sort of strictly between the 2 points. And now for the actual exercise, you could equally write here with the function we consider, your differentiable on x plus 1, and you could close that interval if you want to. This property holds with a closed interval, so you could close it if you want to. And the only thing is that the mean value inequality is, when you take the supremum, you just put the open interval. So you just need to check the differentiability on the open interval. I don't know if that answers your question a bit.
Yes, it does. Thank you.
You're welcome. Yeah. If you basically, yeah, if you wrote a closed interval for any of these properties, everything will be right. You just need to have it open here. One consequence to this property that we can have a look at is that if your function has a bounded derivative on your open interval, then f is k-Lipschitz on the interval. So if we look at the proof, it's just a direct consequence of the mean value inequality. So being k-Lipschitz on your interval means that if you take any 2 points x and y on AB, to be k-Lipschitz, you want to have absolute value of f of x minus f of y smaller than a constant times absolute value of x minus y. And so if you look at the mean value inequality up here, if this term here is bounded, so the supremum here is bounded, then you're k-Lipschitz. And so that's what this property gives you. As soon as you've got a bounded slope, then your function will be k-Lipschitz. And so that's sort of in line with the fact that one of the descriptions of being k-Lipschitz is your function can't vary too much in too short a time. Basically, its slope can't be too big at any given point if you want to be k-Lipschitz. Yeah, so that's a consequence to the mean value inequality, and we can apply the mean value inequality and get some properties related to function monotony. So most of these statements actually are things that you've seen before. So if we sort of summarize on various things that we've seen, if you take a function that's continuous on a closed interval, differentiable in the open one, then you've got the following statement. Your constant on AB, if and only if f prime is equal to 0 on AB. So that's the first thing. And then you've got the following links between being sort of positive derivative and being monotonous or negative derivative. So we know that if you're non-decreasing on AB, that's equivalent to f prime being positive or equal to 0. Non-increasing on AB, you have the f prime smaller than or equal to 0. And these are two things that we keep using. In fact, they're also in the proposition of chapter 6 or 5, I think. If you've got a strictly positive derivative on an open interval, then you'll be increasing or sort of strictly increasing on the closed interval. And if you have f prime strictly negative on the open interval, then you'll be decreasing, so strictement décroissant, on the closed interval. So these are actually two properties that are earlier in your notes as well. Maybe you can just take a second to discuss constant functions a little. If you take a differentiable function whose derivative is 0, is it always constant? So let me just be careful with constant functions. If we take, let me think, example, x maps to, what would it be, x divided by absolute value of x. If we map that function, then you get 1 and -1. You'll get function worth 1 here and -1. Where is this function defined and differentiable?
On R star.
Yeah, absolutely. So if you call that g of x, g defined continuous, differentiable, on R star. And what's the derivative equal to?
0.
Yeah, so for any x on R star, g prime of x is equal to 0. But is this function constant on R star?
No.
No, absolutely. So g is not constant on R star. And what we have written above is that your constant on an interval if and only if f prime of 0, f prime is equal to 0 on AB. Does this here contradict statement 1 of that theorem?
No, because it's constant if we are not passing through 0.
Yeah.
And an interval can't have I don't know how we call it, a hole in it.
Yeah, you can't have a gap in an interval. Yeah, you're absolutely right. That's the really important thing about this statement, is that you've got to really take into account the fact that you're constant on an interval, a, b, if and only if f prime is equal to 0 on that interval. And here, this doesn't contradict, does not contradict point 1 of theorem, what is it called? Theorem 7.57 as R star is not a closed interval. So sometimes you want to make the shortcut saying that f prime is equal to 0 on a domain implies the function is constant on that domain. And that's not true. It's only the case when you're working with sort of intervals. So you've got to be really quite careful with that. Okay. One final thing that we can look at now, that I think will illustrate a little at some point, but that's something that you'll build on in subsequent chapters and years, is the differentiability of an extension. So it's something that's in your notes, and it sort of builds on the fact that we define the fact that you can extend a function by continuity. So I think an example of that was possibly sine of x divided by x. So we've seen previously that we can extend a function by continuity. Okay, example, x maps to sine of x divided by x is defined on R star. It's continuous on R star too. But its continuous extension that we can call G, defined as so G maps x to sine of x divided by x on R star 1 for x equal to 0. Where is that continuous on now?
On R.
Yeah, absolutely. As the limit of this when x goes to 0 is equal to 1, if we just add the sort of point equal to 1, we get a function that's continuous on R. So limit when x goes to 0, the important thing to note of sine of x divided by x, that's equal to 0. Not equal to 0, sorry, it's equal to 1. Yeah, so that was the idea of a continuous extension of a function. And we can extend on the idea. So we can extend on it as follows. Here, an example that I've just mentioned, we had a function that was continuous sort of almost everywhere except at a point. But the limit of the function when that point's reached was finite. So we can add basically a point onto the function and extend it to be continuous. And in a very similar manner, if you've got a function that's differentiable everywhere except at a point, we can want to look at the what would be called the link between what's called the limit of the difference quotient. So this is the derivative and the limit of the derivative. Okay, and sometimes when something happens with this and this, we can complete our function to get a differentiable extension. So we've got a result here, which goes as follows, which really extends on the idea of a continuous extension. So we're going to take a function that we're going to consider on an interval I of R and except at a certain point. So similarly to this, where we don't consider 0 initially, we're going to suppose that the limit when x goes to a of f of x is L. So similarly to above, the limit of sinus of x at 0 is equal to 1, so it's some sort of finite point. So we need that to hold. We also need, however, the function to be differentiable on the interval without a point, and we need the derivative to have a limit at that point. And what then happens is if you add the point to the function, meaning that if you consider f of x with x different from a, so for example r star above, and L if x is equal to a, then you end up with a C1 function on the interval I. No, you end up with a, continuous and differentiable function on the interval I. And if your derivative is continuous, then you get a C1 function. So it's an extension of what we did for continuous functions. And we can do it here if the function's derivative has a limit when x goes to a. So you've got to be able to complete your function with a certain point, and that sort of completion has got to be smooth. So that's how you can do something called differentiable extension. Perhaps we can, if you've got Google at hand, have a look at sinus of x over x, and have a look at whether you think that the extension of that function would be differentiable at 0.
Yes, it would.
Yeah. What
It
do
would be a
you
maximum.
Yeah. What do you yeah, the maximum of sinus of x over x, you're absolutely right. It's at 0 if you consider the continuous extension. What do you think the slope the slope of the function is at 0?
Zero.
Yeah, absolutely. Yeah, it can be proven that the slope of that function is equal to 0. And so yeah, you get a sinus of x over x. If you add the point 1 to the mix at 0, it's actually differentiable. So yeah, you can sometimes add a point and not only get continuity but also differentiability. You can also, if everything's okay, be C1, and you can imagine that you can sometimes extend that to get a C infinite function. Okay, that's the end of the theory related to chapter 7. I think there's just a couple of remarks here, but they're things that we've seen in some examples. So one thing that we saw yesterday, in fact, for one of the inverse functions, is that if you have a, if you have the limit of your derivative equal to plus or minus infinity, then you've got a vertical tangent. So your function is not differentiable A. And if the limit doesn't exist on R, you can use a difference quotient to study the differentiability of F. But yeah, that finishes the theory on chapter 7. So you can see that it's quite dense with lots of different results. So if we look at the notes that we've gone over, related to differentiability, there's the idea of extending a function to be differentiable. There's the mean value theorem and it's the inequality. There's Rolle, and that builds on everything we'd already seen. So that includes inversing functions and the properties related to continuous functions. So we saw Heinz theorem. We saw, what did we see? Blah, blah, blah. Bolzano theorem. There's probably Weierstrass there as well. The intermediate value theorem. So it's quite a dense chapter with lots of new notions. So it's one that if you are in the habit of making flashcards or something for maths, it's one that would probably be good to summarize on flashcards to sort of make sure that you memorize everything, because all of these theorems will come up quite a lot in the next few years. But yeah, that's the end of the theory. Are there any questions on the things that we've covered today?
No.
No. Okay. If there are any, yeah, don't hesitate to ask
I have a
them.
question, but it's
Yeah.
not on today. It's on
Yeah, go
chapter.
on.
Well, it's on. I don't understand the difference between the C0 and the C infinity.
Okay.
that you use.
Oh, let me just get a document. You're welcome. So the question. So what we said. So if you have a function, we've said that. So functions can be C0, C1, all the way up to C infinite, and they're all, that's always on an interval or on a set. So this, let me just get the no, not that. Well, let me just get the part where this was actually studied, and then I'll try and comment on it and give some more examples. So it was back in chapter 5, I think. So where is it? Here. Okay. So it's something that we went quite quickly on. So maybe I'll just copy and paste all of it, and we'll go through it. So the first thing is that all of these notions are based on the idea that your function is either continuous or differentiable. So C0, maybe I don't need that to start with. A C0 function on I is a function that is continuous on I. Let me just shift this out of the way. Yeah. So all C0 is a function that is continuous on I. So for example, some examples, x maps to x squared. That's C0 on R. X maps to sinus of x. That's C0 on R. And maybe one last one, logarithm of x. That's continuous on R plus star. So when we say C0, it's just a shortcut for a continuous function. And we always say that that with an interval or a set in mind. So whenever I write, for example, this belongs to C0 on R, it's just literally because I'm lazy and I don't want to write continuous on that set, and it's a nice shortcut to use. So that's C0, but we can generalize this to further sort of levels of, they're called levels of regularity, really. So if we now look at C1, a C1 function on I is a function that satisfies a certain number of properties. It needs to be continuous on I. So C1 function on, I can't write, on I is continuous on I, differentiable on I, and its derivative is continuous on I. Okay, so you need all of these three properties to hold for your function in order for it to belong to C1. And for example, if you take a polynomial function, a simple one, x squared, that would be C1 on R. It's continuous on R. This is differentiable on R because this derivative is 2x. And its derivative is continuous because 2x is continuous on R. Okay, that's C1. And we can sort of generalize this idea. So if I just write out what C2 means, but we don't use the CK type classes that much yet, but a C2 function on I is basically C1, meaning that all the properties for the C1 functions hold, so it's continuous, differentiable, and its derivative is continuous. But it's also, wait a minute, C1, you continuous, differentiable, it's twice differentiable. So its derivative is differentiable. And that yields a second derivative. And its second derivative is continuous. Okay, so C0 is just continuous. C1 means you're continuous, you're differentiable, and your derivative is continuous. C2 means you're continuous, differentiable, continuous derivative, your derivative is differentiable, and the derivative of the derivative is continuous. So basically the number that's here, when you have CK, means that basically all of your derivatives exist up to the kth derivative, and the kth derivative is continuous. Is that clear for when you have a finite number here?
Yes, thank you.
Okay, and when it comes to C infinite, a C infinite function basically a C infinite function on I is a function for which you can repeat this process an infinite number of times. Basically, no matter how far you take the derivation, let me see if it's written below. Yeah, it's not really very clear here, but you'll be in the C infinite space if you're in the CP space for all P. Basically, no matter how many times you derive your function, you keep reaching a continuous function, and you can keep deriving. So a C infinite function is CK on I for all K on N. For example, a polynomial, if you take x squared, but you can take any polynomial you want, what happens is that's always defined and continuous on R. Its derivative is then defined continuous on R, will be differentiable, and at some point you'll reach a derivative that's equal to 0. And that's always continuous and differentiable, and you stay stuck at 0. But you can repeat this process, you can repeat this process as many times as you want. So it belongs to, so x max to x squared is C infinite on R. And most of the functions that you know are C infinite on their definition domain. You've basically got to work at it a bit to construct functions that are sort of classical functions, but that aren't C infinite. So you've got all of these things here. Polynomials are C infinite, rational functions too, exponential functions too. Yeah, as I was saying, you've really got to work at it to construct functions for which things start to go really quite wrong. But yeah, and a lot of the times, maybe just one side note before we take the break, a lot of the times, if you're asked where a function is continuous, define continuous and differentiable, sometimes I'll just write f belongs to C infinite of R, and that is sort of an answer to the fact that it's defined continuous and differentiable on R, and it sort of summarizes it. It's quite a lazy way of writing things. So yeah, it's just a notation to summarize a bunch of properties. Okay.
Thank you.
You're welcome. We can take the break now, and after the break we'll take a look at some exercises. Are there any other questions related to the chapters, other chapters? Because I can answer some today if there's anything that's come up that is unclear. Don't hesitate to ask them. But if not, yeah, we can take a break and we'll do, I think, where are they? Exercises 12, 13 we'll finish 6 and probably do 7 today after the break. So I'll see you in a little bit. Where am I? Actually do some exercises. So I'm looking for, yeah, we're going to look at exercise 12 that will allow us to use the mean value theorem that we just mentioned during the first class. So I don't want that. I'll look at this. So can you see my screen okay this time?
Yes.
Okay, great. So I'm going to look at this exercise here. I'm going to prove some inequalities. So both these inequalities will be based on the mean value theorem that we're going to exploit. One of them is going to be linked to the cosine function, and the other one we're going to link to the logarithm function. And I think the second question will be very like an example that we did in class a few minutes ago. So what we're going to do is get started with the first question. So what we want to do here is use the mean value theorem for an equality with cosine, with the specificity that we're going to set x on this sort of strange interval here. So we're going to set some point x between 0, with 0 excluded, and pi over 2. We can apply the mean value theorem. So if I write MVT is the mean value theorem to cosine on the segment 0x. Okay, so x here is any value between 0 excluded and pi over 2 included. And we're going to apply the mean value theorem to cosine on that interval. So if you have the mean value theorem at hand, what assumptions do you need a function to satisfy to apply the mean value theorem?
Be continuous on the interval.
Yeah, absolutely. So we need let me see. So we can apply the mean value theorem indeed. That's not a good idea. Cosine is continuous on 0x. Again, I could have equally written that as cos belongs to C0, 0x. What other property do we need?
It has to be differentiable on the interval, but the interval without the extremes, not included.
Yeah, exactly. So we need to be differentiable on the sort of open interval, so on 0x, but we don't need the bounds to sort of be included. And of course, one thing that we can note is that cosine is actually continuous and differentiable on the whole of R, and it's even C infinite on the whole of R. But we just need these two specific properties. What does the mean value theorem tell us then?
That f of x minus f of 0 is equal to f prime of c times 0, x minus 0.
Absolutely. So what we have is cosine of x minus cosine of 0 equal to cosine prime of some c, k times x minus 0. So it doesn't seem that closely linked to what we want to prove yet, but we'll see that we'll be able to exploit it to prove what we want. So c will be in the open interval 0x, and there exists some c, we don't know much about it, such that the equality here, I'll shift it to make it a bit clearer, holds. Okay, what's cosine of, yeah, go on.
Is it important here with the I can't remember what you called them, the Ferenyi and there exists
Oh,
Is it important if it's before or after the equation? Is it the there exists a C that defines the equation, or is it, or does it not matter?
I suppose strictly it's better to write it before. But you could equally, to be honest, you could, something that I tend to write would be for some, I'd put it after and I'd just write it with words for some C and 0x. So I guess it's not that important here, is probably the best answer. But no, the best answer is probably to write it like this. So to write it in that order, but I don't think it's that important in this specific case. Yeah. So we get this equality. Now, what can we say about cosine prime of C?
It's sine of C.
Are you sure it's sine?
Minus sine of C, sorry.
Yeah, no problem. Yeah, it's minus sine of C. X minus 0. Okay, so what we can do is maybe rewrite this a little now, because we've also got cosine of 0 equal to 1. So if I just rewrite the fact, use the fact that that's equal to 1, we get cosine of x minus 1 equal to minus sine of C times x. And what do we actually want to bound in our exercise? It's written above here.
1 minus cosine of x.
Yeah, absolutely. What we want to do is get some sort of upper bound for 1 minus cosine of x. And with this thing that we've rewritten, you can probably see that there's something on the left-hand side here that's very close to, I guess, what we want to deal with. And one thing that we can do to make things even closer to what we want is just multiply by minus on each side. So you get 1 minus cosine of x, and that gets rid of the minus sign on the right-hand side. So we've got, sine of C times x. So we're almost there in the sense that we want 1 minus cosine of x smaller than x, and we've got 1 minus cosine of x equal to sine of C times x. So hopefully we'd like to be able to say something about sine of C that would help us get this inequality here. But what we have is C belonging to 0 of x, with x belonging to, I think, 0 pi over 2. So C can basically be anywhere between 0 and pi over 2. Can we say anything about the sign of, or the values of sine of C for C between 0 and pi over 2?
It's between 0 and 1.
Yeah, absolutely. So 0 strictly smaller than sine of C, smaller than 1. And so this gives us enough information to conclude. So if I refer to this as sort of star, and combined with star, we get 1 minus cosine of x equal to sine C times x. But that, because sine of C is smaller than 1, is simply smaller than x. Okay, and that here is exactly the inequality that we wanted to prove. And that holds as soon as we have x between 0 and pi over 2. So that's one quite classical example of an application of the mean value theorem. And we're going to do another application for a logarithm-based function. So we're going to try and prove a statement above. So it's up here, based on logarithm of 1 plus x divided by 1 minus x. So that's what we are going to look at, and we're going to study this function here in order to get a couple of bounds on the logarithm function, and then we're going to apply it to some numerical values. So we want to set x in 0, 1. And we want to look at logarithm of 1 plus x divided by 1 minus x. So we're going to try and apply the mean value theorem. So we want to the mean value theorem to t maps to logarithm of 1 plus t divided by 1 minus t for t on 0x. Now, if we want to apply the mean value theorem, similarly to what we did above, we need to make sure that this function is actually A, well-defined, and then continuous and even differentiable on the sort of areas that we're looking at. So what do we need to check if we want to analyze where this function is sort of well-defined?
We need to check that 1 plus t divided by 1 minus t is greater than 0.
Yeah, absolutely. So we first let me rewrite that another way. So let's call this f of t for simplicity. F is defined on a subset of R such that 1 plus t divided by 1 minus t is strictly positive. And there are different ways to find that. One way you can do it is through a sign table. So if you look at the sign of 1 plus t and 1 minus t, then you can work out the sign of the ratio. So I need a bit more room up top. If we try and do that, we're going to have two sort of critical points. So you can go from minus infinity to minus 1 to 1 to plus infinity. And so I have 3 columns. 1 plus t is negative and then positive. 1 minus t is positive up till 1, I think, and then negative. And so you get negative, positive, and negative. And in particular, we need to exclude this value because the denominator just explodes at that value, and we'll get 0 here. So where are we going to look at 1 plus t, 1 minus t if we want it to be well defined? If we want the logarithm function to be well defined?
Yeah, t has to be between -1 and 1 excluded.
Yeah, absolutely. So what we see here is, so f is defined and continuous and differentiable for t belonging to -1, 1 with -1 and 1 excluded. So that's the first step. And what we want to do, if we come back to what we're going to try and do is we want to apply the mean value theorem to our function f, but for t between 0 and x, for x between 0 and 1. So does the interval that we're looking at satisfy this property?
Yes.
Yeah, absolutely. No matter
It
what
depends
value.
on
Go on. Yeah.
it depends on x, but in the worst case it would be 0 to 1 excluded, so it would still be okay.
Yeah, absolutely. Yeah, even in the worst case, it's still okay. So what we have is the closed interval 0x by construction with the values that we take for x. It'll be included in -1, 1. So what we can then state is that f is continuous on 0x with the bounds sort of included, and f is differentiable on 0x, and of course you could also write this differentiable with the closed sort of bounds, but for the mean value theorem we only need it to hold for the open interval. So through the mean value theorem, just as above, we know that there exists some c belonging to the open interval 0x, logarithm of, or rather I'll write it with f of x minus f of 0 is equal to f prime of c, x minus 0. So that's a first thing that we sort of get, and we want to further exploit this. So f of x, we can express it as follows. So it's logarithm of 1 plus x divided by 1 minus x. F of 0, so f of x is, we have an expression for it. F of 0, if you have a look at what it's equal to, is equal to logarithm of 0. So we have f of 0 equal to, sorry, logarithm of 1 rather, that's equal to 0. And what we need to also check is f prime of c. We need to derive the function logarithm of 1 plus t divided by 1 minus t. So it's logarithm 1 plus t divided by 1 minus t. And all of that, we need to derive it. So how do you derive this sort of composite function?
With the chain rule and then the quotient derivation.
Yeah, absolutely. So we've got basically the logarithm of a function of t. So it's going to be, if you use what you know for the derivative of the composite logarithm, you end up with f prime of t divided by f of t. If f is the function inside, which it isn't here. So you end up with 1 plus t divided by 1 minus t prime divided by 1 plus t, 1 minus t. So we just need to derive that fraction now, and we end up with 1 minus t plus 1 plus t divided by 1 minus t squared. And if we want to divide by the ratio that's underneath, you can multiply by 1 minus t and divide by 1 plus t. Hopefully it will simplify, so that and that simplify. And then what else do we, if we take t in -1, 1, which is where we can work, the t terms here simplify, and you should have 2 divided by possibly 1 minus t squared. Yeah, there. So if we now use that for f prime of c and the expression that's above, what do we get for f prime of c?
just need to replace t by c.
Yeah, absolutely. So what we can do is rewrite this, but replacing c by t or t by c. So f of x is logarithm of 1 plus t divided by 1 minus t, minus f of 0, which we showed was equal to 0. And we get that it's equal to 2 divided by 1 minus c squared times x for some c in our interval, which was a 0x. Is that the result that we wanted?
Not exactly, but we know that c belongs to 0 to 1, and so if we plug in these numbers in, we'll have two values.
Yeah.
One for the lower bound and one for the upper bound.
Yeah, absolutely. So we've got an equality here, and you're absolutely right. We know that c belongs to a certain open interval here, so we can bound c and then work with those bounds to basically bound this function. So what we get if we try and do that, we get 0 smaller than c smaller than x, like this rather. That implies that if we take c squared, we'll get 0 c squared smaller than x squared. And that works because everything is positive. And so if we take 1 minus the objects, we need to change the order of everything. So you get 1 minus x squared smaller than 1 minus c squared smaller than 1. And what we then get, if you try and inverse and multiply by 2, we need to swap the bounds again. So you get 2 divided by 1, basically smaller than 2, 1 minus c squared, smaller than 2, 1 minus x squared. But here we have this multiplied by x. X is positive. So we can multiply by x without changing the signs of the inequality. So we'll get 2, 1 minus c squared times x in the middle, 2x on the left-hand side, and 2x, 1 minus x squared on the right-hand side. So what does that tell us about the logarithm function that we're interested in?
It is also bounded by 2x and 2x divided by 1 minus x squared.
Absolutely, yeah. We've got the equality here above, and we've got this term here, just here. So we've got 2x smaller than logarithm of, that should be 1 plus x. So, 2x smaller than logarithm of 1 plus x divided by 1 minus x, smaller than the term on the right-hand side. And hopefully, let's have a look. That's what we wanted to prove. Yeah. Okay. So that's the first part of the question. So we've proven some bounds on logarithm of 1 plus x, 1 minus x, and that holds for x belonging to, if we have a look, open interval 0, 1. Okay. And I think in the next part of the question, we need to look at some specific values. So these specific values are here. We want to use that to find some bounds for logarithm of 5 over 3 and logarithm of 3 over 2. How do you think we can apply this to bound, for example, logarithm of 5 over 3? So what we've got here is if we take looking at logarithm of 1 plus x, 1 minus x for x in this, we've got some bounds. And if we can basically find x such that 1 plus x over 1 minus x belongs to 5 over 3, and the x in question belongs to 0, 1, then we can apply this inequality here. So what we can search for is that if we need to search for an x such that 1 plus x divided by 1 minus x is equal to 5 over 3. And so we've got some sort of equation to solve, and so that's equivalent to 3 plus 3x equal to 5 minus 5x. And if we just rearrange things a little, we should have 8x on the left hand side and 5 minus 3, so 2 on the right hand side. So we get x equal to 1 over 4. And that belongs to the open interval 0, 1. So 5 over 3 is equal to 1 plus x over 1 minus x for x equal to 1 over 4, which belongs to the open interval here, for which this inequality holds. And we can apply the the inequality above using previously proven inequality. We get 2 times 1 over 4, so 1/2, smaller than logarithm of 5 over 3, smaller than 2 times 1 over 4 divided by 1 minus 1 over 16. And if you compute the two values here, we'll get 1/2 on the left hand side, and here we'll get a 1/2 divided by 15 over 16. And so if we try and rearrange that, we get 1/2 times 16 divided by 15. So we'll get 16 over 30, so 8 over 15. There we go. So we get 1/2 smaller than logarithm of 5 over 3 smaller than 8 divided by 15. So that's one part of the questions where we apply this inequality. And in the second case, we can do the same for logarithm of 3 over 2. So if we look for bounds for logarithm of 3 over 2, we can proceed in the same way. Okay, so what x would you get if you're trying to get 1 plus x divided by 1 minus x equal to 3 over 2?
I have x equal to 1 over 5.
Yeah, absolutely. I think that's the answer. So you should end up with 2 plus 2x equal to 3 minus 3x. And yeah, it looks like you get 5x on the left hand side equal to 1. So you get x equal to 1 over 5. And that belongs to 0, 1. So we can apply the inequality above. Therefore, logarithm of 3 over 2 will be greater than 2 over 5. And on the right hand side, you'll have 2 over 5 times 1 divided by 1 minus So x 1/25. Let's reduce that, so we get 2 divided by 5. You get 25 and 24 possibly. So we get 1/12 times 5. 5/12, which isn't what I'm looking for. Oh yeah, it is. Yeah, it is. And what we conclude from this is 2/5 smaller than logarithm of 3/2, smaller than 5 divided by 12. So using the mean value inequality here, we can get some sort of bounds for values of the logarithm function. So it can be quite a powerful tool if you ever want to get approximate values for different functions, and the mean value inequality sometimes helps with that. Yeah, so that's an application of the mean value inequality, or mean value theorem rather. Are there any questions on what we've just done?
No.
Okay. If there aren't, one thing that we can turn to doing now is finishing exercise 6. So it's an exercise on the inversion of the hyperbolic sine function, and it's an exercise that we did that we started yesterday. So if I just copy and paste what we did yesterday, so we've got everything at hand. Come on. We'd started to answer the questions, and we had a couple left, I think. So we were looking at SH of x. We'd shown that it was a bijection, and so we denote as arg SH the inverse. And we'd shown that the function was odd, as SH is odd, and we computed the bounds of the function at the bounds of the definition domain. So we roughly had this. There we go. And we wanted to study the differentiability of the inverse of SH, and we wanted to, once we'd studied the differentiability, actually compute the derivative. So that's where we were. So we're looking at the derivative of an inverse function. And where is the derivative of an inverse function defined?
On the images of the non-inverse.
Yeah, it's basically, it's differentiable anywhere where the original function is differentiable and where the original derivative is not equal to 0. So what we know in particular for SH is SH is differentiable on R, and for any x on R, SH prime of x, which is CH of x, is not equal to 0. In fact, so SH prime of x is CH of x, and CH of x is always greater than or equal to 1. So there are no points basically of R at which SH prime is equal to 0. And so arg SH is differentiable on the whole of its definition domain, so that's R as well. So what we're going to do now, we're going to take some y in R and compute arg SH prime of y. So if we apply the formula that we have for the derivative of an inverse function, what we have is 1 over f prime, where f is the original function. So that's 1 over ch of the inverse function of y, so arg sh of y. That's what you get if you just apply the formula. And it may be that we can simplify this quite a bit. So is there anything you might be able to say about this term here? Oh, what we can say is see. Yeah, go on.
I'm not sure exactly, but wasn't there is 1 equal to hyperbolic cosine squared minus hyperbolic sine squared?
Yeah, absolutely. So we have this. We have ch squared minus sh squared equal to 1. You're absolutely right. And so here, and we also have ch of x greater than 1 x on r. So in particular, ch is positive. And so this is equal to the square root of ch squared, arg sh of y. And once we're there, what was just said is key. So we get square root of 1 minus, oh sorry, plus sh squared of arg sh of y. And what can we now say about that?
It is equal to square root of 1 plus y squared.
Absolutely, yeah. So that is square root of 1 plus y squared. So we conclude that for any y in R, arg sh of y prime is equal to 1 divided by square root of 1 plus y squared. And so once again, we've got a function for which the derivative is actually quite an explicit function, whereas the original one is the arg sh in itself isn't too explicit. So that's question 3. And what we're going to show in the final question is that for any x on J1, where J1 we showed that it was equal to R, we have arg sh of x equal to this explicit expression here. So what we're going to work with is the definition of the inverse, and in particular use the fact that it's the inverse of a function with lots of exponentials in it. So if we let x on R, arg sh of x is equal to some value c, that's equivalent to x is equal to sh of c. And what's sh of c equal to? If you look at what we
arg sh of x.
Yeah, you can do that. You've also got an exponential expression for sh that's explicit. You end up with x equal to exponential of c minus exponential of minus c divided by 2. Okay, so you get x, if we perhaps just move the 2, we get 2x equal to exponential c minus exponential of minus c. And one thing that we can do here is multiply everything by exponential of c, and perhaps shift everything to the same side of the equation. So we'll get exponential 2c minus exponential minus 1 actually, minus 2x exponential of c. Okay, so we've given ourselves some x and r, which is some sort of data, and we want to rewrite argsh of x and get some expression for c here. And what we can see in this equation, sorry, that's equal to 0. So x is fixed, and we want some data basically on c. And if I rewrite this again, we get exponential of c squared minus 2x, where x is some sort of fixed information, times, so minus 2x exponential of c minus 1 equal to 0. And we can rewrite this as y squared minus 2xy minus 1 equal to 0, where y is equal to exponential of c, and is in particular is strictly positive. Is there anything, once you're here, is there anything that you could do to try and find some expression for y? Does this resemble an object that we know about, albeit sort of under some sort of strange form?
Well, we could compute the delta.
Yeah, absolutely. That looks like a bit. Looks like a polynomial. If you forget about the fact there's some sort of x here, I mean, x could be equal to 1, for example. That's a polynomial in y. So we could compute the delta. So we get b here is basically minus 2x. So we get 4x squared minus, so plus 4 times 1 times 1. So delta is equal to that, and that's 2 times, no, what am I saying? It's 4 times x squared plus 1, and that's strictly positive. So y, if we want to compute the roots of this equation, we can write delta under the form 2 times x squared plus 1 squared, and y is equal to, so it's either 2x minus 2 square root of x squared plus 1 over 2. We want a shorter line than that. Or y is equal to the same thing with a plus sign between. So you get 2x plus square root of x squared plus 1 with a 2 divided by 2. So that's x minus square root of x squared plus 1, or x plus square root of x squared plus 1. But we know that y has to be positive. And can we say anything about the signs of these two expressions for y?
The first expression is negative because x square root of x squared plus 1 is greater than square root of x squared, which is greater than x.
Yeah, absolutely. So we've got the following thing. That's strictly negative, as basically x is smaller than absolute value of x equal to x square root of x squared, and that's smaller than square root of x squared plus 1. So that's negative, and this is positive. So what's y equal to?
To the second expression?
Yeah, absolutely. So therefore y, which was equal to exponential of c, will be equal to x plus square root of x squared plus 1. Okay. And if you come back to the start of this exercise, we'd given ourselves some x in R, which is some fixed data, and we'd said that argsh of x is equal to c. And so here we've got some information on exponential of c. So can we deduce some information on argsh of x from this?
If we applied the logarithm function,
Yeah, absolutely.
we get c is equal to logarithm of the right-hand term.
Yeah, that's absolutely right. So if we apply the logarithm function, we're allowed to here, because this here is strictly positive, we get c equal to logarithm of x plus square root of x squared plus 1. And if we use the fact that argsh of x is equal to c, we get argsh of x equal to the logarithm. And so we've got an explicit expression for basically argsh of x. So you start off by writing what by calling c the value of argsh of x, then you apply the fact, you imply the inverse to link x to c, and you're in a setting where you can write some sort of polynomial equation and get some information about c, basically. This type of reasoning isn't always possible, but with the hyperbolic trig functions, it often is possible. And we've got some sort of explicit expression. Okay, so I think that concludes the exercise on the hyperbolic sine function. And what we'll be able to do to finish a class today is work with the hyperbolic cosine function. And I think in this case as well, we've got an explicit expression. So we'll perform reasoning that's very similar to what we've just done. And once again, if you take the table from your notes where you've got all the classical functions, you can add this information onto it if you want, especially related to the derivative. This derivative here is quite useful at times to compute some primitives especially. So it's one to know, and you can add it to a list of classical functions. So that's exercise 6. And what we can do is very similarly do exercise 7 here. So you can see that the questions are very similar. First, we're going to show that we can have a bijection. Using that bijection, define the inverse, compute the limits of the function at the bounds of the interval, look at the differentiability, and then come up with some sort of logarithmic expression for argch of x. So the first thing that we can maybe remind ourselves of is what does ch of x vaguely look like if we look at the graph? So if you take a look, I think it's in chapter 5 or 6 we studied it. It's basically x squared but greater than 1. So that's a rough curve of ch. So if you consider ch on the whole of its definition domain, is it a bijection?
No.
Oh, absolutely. So maybe one sort of disclaimer before we start is that ch of x maps to ch of x is an even function. and is therefore not a bijection on the whole of its definition domain. It's not a bijection on R. So what we need to do if we want to compute an inverse of the hyperbolic cosine function is to restrict the interval in which we consider it. And in particular, what's done here is, if you look at the exercises, we're going to look at the application, but only on R plus. And that's how we're going to define the inverse function. It's quite similar if you want to inverse x squared. Basically, you only look on R plus, and that's convention. So we need to show that we've got a bijection on R plus. And so if you consider G2, the maps from x to ch of x on R plus, that's defined, continuous, and differentiable on 0 plus infinity. And what's the derivative of this function? So if you're on 0 plus infinity and you derive ch, you'll get sh of x. Okay, so that's some information we can use to show that we've got a bijection. So we've got the two classical arguments. We've got G2 is C0, so continuous on 0 plus infinity. And for any x on the open interval, ch prime, G2 prime of x is strictly positive. Okay, get sh of 0, so G2 prime of 0 is equal to 0 at 0. But if you exclude 0, then you're strictly positive. So G2 is strictly increasing on 0 plus infinity. So what does that tell us about our function?
It's a bijection on 0
Yeah.
to plus infinity.
Yeah, it's a bijection, exactly, from 0 to plus infinity, or on that interval rather. What remains to be sort of established is what the image set of G2 is. So we can find that by remembering that ch of 0 is equal to 1. And or rather, if I use the notations that are above, get G2 of 0 equal to 1, and the limit when x goes to infinity of G2 of x is equal to plus infinity. So what's the image set of G2 on R plus?
One to plus infinity.
Yeah, absolutely. Therefore, ch of G2 rather is a bijection from 0 plus infinity to 1 plus infinity. And we define its inverse arg ch, that if we have a look at where it maps from, arg ch of x will map from the interval 1 plus infinity to 0 plus infinity. So that's the first step to finding an inverse for the hyperbolic cosine function. So it's using the standard arguments. We show that we've got a continuous function that's strictly monotonous. So it's a bijection. And then we have a look at the values at the bounds of the interval. And we get the sort of the interval that the function maps to. Now, what we're going to do as part of the second question, so J2, if I use the notations in the exercise, J2 here, that's 1 plus infinity. And so what we want now are the limits of argch at the bounds of the interval J2. So the bounds of the interval J2 are 1 and plus infinity. So we basically want argch of 1 and the limit at plus infinity of argch. So how can we find argch of 1?
It's equal to 0, but I don't know how to prove it.
Yeah, you're absolutely right. It's equal to 0. And if we want to prove it, you just need to write that ch of 0 is equal to 1. So argch of 1 is equal to 0, as it does the sort of inverse mapping. And similarly, there's a limit when x goes to infinity of ch of x is equal to plus infinity. We can deduce that the limit when y goes to infinity, perhaps of argch of y, gives us plus infinity as well. So we've got values at the bounds of the domain G2 now, or J2. So that's some further analysis of the inverse of the hyperbolic cosine. And the two questions that are remaining are very similar to the questions that we've just done for the hyperbolic sine function. So first, we're going to look at the differentiability of argch. So what do we need to check to look at the differentiability of argch?
The differentiability of ch.
Yeah, absolutely. So we know that ch is differentiable on 0 plus infinity. Are there any points where the derivative of ch is equal to 0?
Yes, on 0. I mean,
Yeah.
0
So g2 prime of if I call that g2 instead of ch, g2 prime of 0 is equal to 0, and that's the only point where the derivative is equal to 0. If we take any other x on 0 plus infinity, so any x strictly positive, g2 prime of x is not equal to 0. So if we apply the inversion theorem, argch of x is, where can we say that argch of x is differentiable?
on 0 excluded to plus infinity.
You got the right idea, but
on 1 excluded to plus infinity.
Absolutely. So it's the interval where argch is defined, but we need to remove the image of this point here, so the image of 0. So we need to remove g2 of 0. So that's 1 plus infinity. So what we can now do is compute the derivative of argch. So what we're going to take is for any y greater than 1, argch prime of y. We're going to apply the formula for the derivative of an inverse function. So it's going to be, if we consider f to be our initial function, we're going to have f prime applied to the inverse function. So here we'll have ch prime, so sh, applied to argch of y. That's an initial expression for our inverse function, or our derivative, sorry, of the inverse function. But we're going to try and rewrite this. How do you think we may be able to rewrite this? Okay, one
Maybe
key is,
by
yeah,
taking
go
the
on.
square of it, and then I think we can replace it by th of arg th of y minus 1.
Yeah,
over the squares.
absolutely. Yeah, absolutely. So we're going to try and use the same procedure as we did earlier. We just need to check that this thing here is positive, because otherwise we can't write it as a square root of a square. If we have a look at the value of argch of y will be greater than 0. So sh of argch of y greater than 0. And what that means is that we have argch of y is equal to the square root of sh squared applied to argch of y. And then we can just roll out the same technique as the one we used earlier. So sh squared is, if you use the fact that, so ch squared minus, I'm going to get this the wrong way around, I think. Let me check. Yeah, ch squared minus sh squared is equal to 1. So sh squared is ch squared minus 1. So that's equal to ch squared of argch of y minus 1. And so we get square root of y squared minus 1. And so for any y greater than 1, argch prime of y, that's 1 divided by square root of y squared minus 1. Okay, so that is the expression for the derivative, and as you can see, it's the same method as what we did a minute ago for the hyperbolic sine. And again, similarly to what we did a minute ago, what we can do to finish this class is find a logarithmic expression for argch of x. And as you can imagine, we're going to use a very similar technique to what we did for the hyperbolic sine function. So we're going to let some x belong to the definition domain of argch, that's 1 plus infinity. And we're going to say that argch of x is equal to some c. And we're going to try and express some something for c. So that's equivalent to ch, so x equal to ch of c. Again, ch of c is exponential c plus exponential minus c divided by 2. And if we use the same principle again as earlier, we can reach a polynomial function. So we've got, or a polynomial type equation rather. So we've got 2x equal to exponential of c plus exponential minus c. And if we multiply everything by exponential of c, we'll get exponential of 2c plus 1 minus 2x exponential c equal to 0. And we can say that that's y squared minus 2yx y plus 1 equal to 0, y equal to exponential of c. So y is positive, and y will be a root to a certain polynomial equation. So it's a similar one to earlier. The delta is just slightly different. So delta, if you compute it, you get 4x squared minus 4. So that's 4x squared minus 1. But what we can see here is that x is in 1 plus infinity. So that's greater than 0 as x belongs to 1 plus infinity. Okay, and we can apply the root formula. So y is equal to either x plus square root of x squared minus 1, or y is equal to x plus, I wrote it underneath, or y is equal to x minus square root of x squared minus 1. So it's one of these two, and we want the case where the exponential is positive. Sorry, the value on the right hand side is positive. Can we say anything about the values of these two terms? Or the signs of these two terms?
I think both of them are positive.
Yeah, it's not that, yeah, that you're absolutely right. Both of them are positive, so it's not that clear this time. So this one's definitely positive because x is greater than 1, so this is definitely positive. And this, you can reason with it and show that this is also positive. So we're a bit stuck here to find which one of these two solutions is the right one. So we have exponential of c equal to x plus square root of x squared minus 1, or exponential of c equal to x minus square root of x squared minus 1. So we're a bit stuck here when it comes to deducing which is the right solution. So we can press forward a bit, and we get c equal to the logarithm of x plus square root of x squared minus 1, or c equal to the logarithm of x minus x squared minus 1, because this is positive, and this is positive too. But we need to make a choice between the two values. So, do you have any idea about how we can do that?
We should take the first one because the second one is negative, and we know that the arc th should be positive.
Yeah, absolutely. So what we need out of these two expressions, so c is arg ch of x, and we know that arg ch of x is a function with positive values, but c equal to arg ch of x is greater than 0. And what we have, if we take the second one, so logarithm of x minus square root of x squared minus 1. If we want to check whether that's positive, we need x minus square root of x squared minus 1 greater than 1. And if we go any further with this, we can rewrite it as an equation. So we get x minus 1 needs to be greater than square root of x squared minus 1. And if we take the square here of both these sides, because everything I think here is, everything here is positive, so we can take the square. X is greater than 1, so that's equivalent to x squared minus 2x plus 1 greater than x squared minus 1. And that should simplify the expression a bit. We'll get x squared minus x squared, so those two terms disappear. We get minus 2x greater than minus 2. And so x probably needs to be smaller than 1. So what issue do we get in this setting?
The x is between 1 and plus infinity. So
Yeah, absolutely.
It can be smaller than 1.
Yeah. But x was defined to be greater than 1, so logarithm of x minus square root of x squared minus 1 is not a possible expression. And we deduce that argch of x is the logarithm of the second term, so it's x plus square root of x squared minus 1. So in this setting, we applied the same methodology as for the hyperbolic sine function, but for the hyperbolic sine function, it became apparent when expressing exponential of c. In one case, it was equal to something positive, in the other case, it was equal to something negative. And so the choice was made at that stage as to exponential of c equal to the term that was positive. So the other possibility just wasn't, we couldn't have that. Here, both of these terms are positive. You can show that they're positive. And so we need to decide in some other manner, but one of these expressions gives values that basically aren't possible, that aren't coherent with the argch function. And so that allows us to make our choice. And we get this expression for the hyperbolic cosine inverse function.
Excuse me.
Yeah.
I'm not sure. How do we know that ln of x minus square root of x minus 1 is positive?
Oh yeah, that's a good question. What we want is, let me see, wait a minute. What we've done is we've set c equal to argch of x, and argch of x, by definition, it maps from 1 plus infinity to, where is it? 0 plus infinity. So the values that it maps to should be positive. In fact, you can, how can I put it? You can, so we want to check that the values here can be positive, and in particular strictly positive. I think if you take x equal to 1, in both cases, these two expressions are equal. And so the problem is getting values that are strictly positive. And so that's why we solve this equation. If you solve this equation, we want for this to be coherent with argch of x. We want this to have positive values, and if you solve this equation, you get x smaller than 1. But by definition, with what we've worked with, we know that x has to originate between 1 and plus infinity, as argch of x maps 1 plus infinity to positive values.
Okay, thank you.
You're welcome. Okay, so it's slightly more subtle this time, but you still reach a logarithmic expression for the hyperbolic cosine inverse. So these expressions here aren't things that you need to know. Rather, it's good to have in mind that these two functions do have explicit expressions. The things that are important are the the derivative of the inverse function, and some of the properties of the inverse function, and to know that there is a method to compute an explicit expression. But we can stop here for today. Are there any other questions on what we've done?
No.
Okay. If there are any, or if there are any questions related to the test, don't hesitate. I've got emails, I think, asking whether it's on Zoom or at INSA. It will be on Zoom just like last time. Yeah. So we can stop here for today, and I think we've got class on Monday, so I'll see you then.